Assalamualaikum and good day. In this lecture video, we will look into reaction mechanism. At the end of this lesson, you should be able to predict the rate law from the reaction mechanism. An overall balanced chemical equation does not tell us much about how a reaction actually takes place. In many cases, it merely represents the sum of several elementary steps or elementary reactions, which is a series of simple reactions that represent the progress of the overall reaction at the molecular level. The term for the sequence of elementary steps that leads to product formation is reaction mechanism. The reaction mechanism is comparable to the route of travel followed during a trip. The overall chemical equation specifies only the origin and destination. As an example of a reaction mechanism, let us consider the reaction between nitric oxide and oxygen. We know that the products are not formed directly from the collision of two NO molecules with an oxygen molecule because N2O2 is detected during the course of the reaction. Let us assume that the reaction actually takes place via two elementary steps as follows. In the first elementary step, two NO molecules collide to form a N2O2 molecule. This event is followed by the reaction between N2O2 and oxygen to give two molecules of NO2 or nitrogen dioxide. The net chemical equation, which represents the overall change, is given by the sum of the elementary steps. Species such as N2O2 are called intermediates because they appear in the mechanism of the reaction, that is the elementary step, but not in the overall balance equation. Keep in mind that an intermediate is always formed in an early elementary step and consumed in a later elementary step. Molecularity and rate determining step. The molecularity of a reaction is the number of molecules reacting in an elementary step. These molecules may be of the same or different types. Each of the elementary steps discussed before is called a bimolecular reaction. An elementary step that involves two molecules. Unimolecular reaction is an elementary step in which only one reacting molecule participates. Very few thermomolecular reaction that involve the participation of three molecules in one elementary step. The simultaneous encounter of three molecules is a far less likely event than a bimolecular collision. When we study a reaction that has more than one elementary step, the rate law for the overall process is given by the rate determining step, which is the slowest step in the sequence of steps leading to product formation. An analogy for the rate determining step is the flow of traffic along a narrow road. Assuming the cars cannot pass one another on the road, the rate at which the cars travel is governed by the slowest moving car. Experimental studies of reaction mechanism begins with the collection of data or rate measurement. Next, we analyze the data to determine the rate constant and order of the reaction, and we write the rate law. Finally, we suggest a plausible mechanism for the reaction in terms of elementary step. The elementary step must satisfy two requirements. The sum of the elementary step must give the overall balance equation for the reaction, and the rate determining step should predict the same rate law as is determined experimentally. Remember that for a proposed reaction scheme, you must be able to detect the presence of any intermediates formed in one or more elementary steps. Let's consider this example. The reaction between nitrogen dioxide, NO2, and carbon monoxide, CO to produce nitrogen monoxide, NO, and carbon dioxide, CO2, is believed to occur via two steps. The experimental rate law is rate equals to K multiplied with concentration of NO2 squared. What is the equation for the overall reaction? Because NO3 is produced in the first elementary step and it does not appear in the overall balance equation, so it is an intermediate. So we have for the overall balance reaction is NO2 plus CO to produce NO plus CO2. So the intermediate will be the NO3. What can you say about the relative rate of step 1 and 2? Rate is equals to K times concentration of NO2 squared is the rate law for the step 1, so step 1 must be slower than step 2. Rate laws for reactions are affected by the position of the rate determining step in the overall reaction mechanism. As discussed in the previous concept, if the first step or initial step in a reaction mechanism is the rate determining step, the slowest step, then the overall rate law for the reaction is easy to write, and it simply follows the stoichiometry of the initial step. Since the first step is the slowest and the entire reaction must wait for it, so it will become the rate determining step. For example, let's consider this reaction between nitrogen dioxide and carbon monoxide. So the elementary step of the proposed reaction mechanism are represented as the following. Since the first step is the rate determining step, RDS, so the overall reaction rate for this reaction is given by this step. Rate equals to K times the concentration of NO2 squared. So this 2 is, this power of 2 is given by the stoichiometry number. As it turned out, this rate law has been verified with experimental evidence. If the rate determining step is not the first step in the reaction mechanism, the derivation of the rate law becomes slightly more complex. Consider the following reaction. The proposed mechanism is given by step 1 and step 2. Step 2 is the slow rate determining step, so it might seem reasonable to assume that the rate law for this step should be the overall rate law for the reaction. However, this rate law contains N2O2, which is a reaction intermediate, and not a final product. The overall rate law cannot contain any such intermediates because the rate law is determined by experiment only, and such intermediates are not observable. To get around this, we need to go back and consider the first step, which involved an equilibrium between NO and N2O2. At equilibrium, the rate law of the forward reaction will equal the rate of the reverse reaction. We can write this as follows. And for step 2, rearranging for N2O2, we can now substitute this expression into the rate law for the second step, the rate determining step. This yields the following. This overall rate law, which is second order in NO and first order in oxygen, has been confirmed experimentally.